Here are our AB notes for 6-3. So we're doing a lot of the same stuff that we did earlier this chapter. We're still taking differential equations. We're still finding general solutions. Remember, general solution is going to have some kind of constant in there. And we're still using that strategy of separating out our variables. So the first thing that we notice here is that we have x and y together over on the right. We're going to have to divide both sides by y. We want to get the y over here. We're going to have to multiply both sides by dx. So maybe I'll do that part first. And I'm going to start over here so I have plenty of space. So x squared plus 4. So I'm leaving the x squared plus 4 for now. That's fine. I don't want to do too much at once if it's going to be confusing. So I know I'm dividing both sides by y. So I'm going to have dy over y. And then I know I am multiplying both sides by dx. And now I have x dx. So we're using that Leibniz notation that we seem to prefer. And now to finish getting my y's by themselves, I'm going to want to divide by this on both sides. So dy over y equals, and this makes me think when I have dy over y, remember that's going to be natural log when I integrate. On the other side, we'll have x over x squared plus 4 dx, and we want to integrate both sides. So let's go ahead and set that up. So like I said on the left, I know this is going to be the natural log of y. That's easy. But on the other side, I'm going to have to play around with it a little bit. So my denominator has an x squared plus 4. And if that was my u, my du would be 2x dx. So I really need to have a 2 in the numerator. And then I'll have kind of the same thing I have going over on the left, where I have like my du over my u. So let's go ahead and we're going to put in a 1/2. And then make that a 2x instead. All right. And now we're going to go ahead and integrate. So we'll have the natural log of y. Remember when we integrate, because we can only take logs of positives, we have to put absolute value signs in there. On the other side, we'll have 1/2 of the natural log of x squared plus 4. And then what your book is doing is they're labeling these constants throughout, like a C1 or a C2 or a C3. And then in the final answer, they're just making them C. So it's just one of those small kinds of things that your book does with notation. So I've got to continue on over here. So I know that a 1/2 in front is really a square root. So now I've got a natural log of y equals, and if I make this a square root, I no longer need absolute values. So natural log square root of x squared plus 4. And then there's a plus c out here. And I want to exponentiate both sides. So I'm going to raise both sides as a power of e, because I do not want to have that natural log there. And then remember, if I have e being raised to this entire thing right here, I can really, and I guess I called that a C1, I can really make this e to the natural log of the square root of x squared plus 4 times e to the c plus 1 power. So because those are the same base, I could add my exponents and put them back together. So this is just a different way of writing that. And what that's going to allow me to do, and over here I just have absolute value of y, is now I'm going to put this in front. And then because I had an absolute value, I'm going to have a plus or minus here. Remember, this is gone. Now I have a square root. And basically, I'm going to kind of absorb all of this as just one constant and just call it c times the square root of x squared plus 4. So I know in the past we've always had that plus c at the end. And now that we're using e like this and we're having to like log both sides or exponentiate both sides, it's definitely changing some things. So this is what we have here. One of the other things that they talk about is looking at the original and making sure that like y and x can be 0. So if I had like a y in the denominator right away, I would know that y couldn't be 0, and I might have to account for that in some way. So on the next one, we are finding a particular solution. So our steps for that is we're still going to separate our variables out, and then we're going to integrate again. And then we're going to use our initial conditions to solve for c. And there could be more than one constant. So I'm going to just write use initial conditions to find constants. Okay, so what we have going on, this one looks absolutely like a mess. So I see I've got a bunch of stuff with X and Y all kind of multiplied here, and I've got them multiplied over here. But the big issue is that plus sign. So what I want to do is I want to subtract this piece to the other side, just because it's shorter looking, and I want the dx over on that side anyway. So then I would have e to the negative x squared times y squared minus 1 dy equals, and really I should have this started probably over on the left further. I'm going to run out of space. I have negative xy dx. And now to get all my y's on one side and my x's on the other, I'm going to have to divide both sides by this y, and then I'm going to divide both sides by e to the negative x squared power. So when I divide by y, and remember this will be gone, so I'll have y squared minus 1 over y dy. And then on the other side, so now this y is gone. Remember, I divided both sides by y. And then I'm also going to divide by this part. So I'll have a negative x over e to the negative x squared dx. So what I kind of noticed setting this problem up is, first of all, I have something with a negative exponent in my denominator. So that doesn't need to be in a denominator. I could just make it e to the negative x squared times negative x dx. And really, if this is an x squared right here, my derivative of x squared is of, actually that's not a negative anymore, is it? Let's fix that. My derivative of a positive x squared is just going to be a 2x. So I really want this to be a 2x right here. So I'm going to put the negative and a 1/2. I did not leave myself any space in front. So I'm pulling this negative out because I don't need it in the middle of the problem, and because I want a 2 to be there because that's the derivative of my exponent, I need to account for that by putting in a negative 1/2. So on the other side, I know when I have a fraction that's bigger on top, I just want to divide it through by that denominator. So I need to think about this as y squared over y minus 1 over y. And this is dy. I feel like this is getting really messy. So y squared over y is just y. And then I have minus 1 over y. So that side's all set. Other side's all set. I could have gone ahead and integrated on the right, but I like to do it all at once, so it's pretty. Okay, so now we're ready to integrate. So on the right, I'm just going to have a negative 1/2 e to the x squared power, and then plus some kind of constant. And then on the left, when I integrate y, that's first power. So that's going to be power rule, y squared over 2. And then this is my dy over y, basically. So that's going to be a natural log of y. So this is kind of a mess right now. That's what it looks like. And I guess I wouldn't really need to make this a C1. It could just be a C. But what I'm going to do right away, before I even try to make this look prettier, is I'm going to use those initial conditions. So I worked on separating my variables out. We went ahead and integrated. And we're working with E an awful lot. So I could see where if you have been struggling this semester, there's been so many rules and they've happened so fast and there's so much to remember, and we're still using them all the time in this chapter. So it's just getting more difficult. All right, so let's see where we're at. So we've got this. Now we want to use those initial conditions, and my initial condition is that y of 0 equals 1. So that means I can plug in a 0 for all of my x's, and my y's are going to equal 1. So let's see what we got here. So y squared over 2 would be a 1 squared over 2 minus natural log of 1. And that's basically saying e to what power equals 1? Well, that's just going to be equal to 0. So I know that already. And then I'm going to have a negative 1/2 e to the, this will be 0 squared power, so 0 power, and then plus my constant. I'm just going to call it c. I'm not going to have to do anything fancy with this one. Since we actually are going to be able to solve for the constant, I don't need to really do any of that weird notation we did on the last one. So let's go through and clean this up. So this is going to be a 1/2. We've already said that the natural log of 1, any log base of anything of 1, is just going to be 0. and e to the first power is 1. So this is a negative 1/2 plus c. So that gives us 1/2 equals negative 1/2 plus c. So 1 is equal to c. So what I could do at this point is I could take this equation here that I have and I could just plug in 1 for c. And it's really ugly, but this is fine. It's not incorrect. It's also very long and it's not wanting to fit in my paper here. But I fit it in there. The other thing that I could do is I could make it prettier. And you know your book is really fond of making things prettier. So if I went through and I multiplied everything by 2, so I didn't have 1/2, then I'd have a y squared instead. And I'd have a 2 times my natural log of y. And then over here, my negative 1/2 would be gone. So I would just have negative e to the x squared power, and then I'd have a plus 2. And then your book is going to say, well, I wouldn't need these absolute value signs if I just put the squared over here. So now we have y squared minus natural log y squared. And then you know what? Why even have a negative over here? If we add the x part to the other side, that e to the x squared part to the other side, then we don't have a negative there. And then we have everything equal to a constant, which looks kind of nice. So your book is going to give answers that are more like this. So the reason I'm telling you, I think this is a really good answer for where we're at right now. But when you check, they're going to give you this. And ultimately, this is a lot prettier and easier to work with. So just kind of keep that in mind while you're checking your answers. We're going to do one more like this where we have given initial conditions. I really like this last one because it's just worded a little bit differently. They don't tell you dy dx. They say to write an equation of the curve. So that doesn't say tangent line, that says curve, okay? And they give us the point and they tell us what the slope is. So I know we're so used to point, slope, and thinking tangent line, but we want to know the original curve. So that means, and this should be the word has, that I need to think about this slope. It's an m, but it's also a y prime, right? That is our slope. So y prime is kind of a pain to work with. We prefer that other notation. So I'm going to say that dy dx equals y over x squared. And what I'm doing is exactly what I've done in the last few problems. This is my differential, and I need to find a particular solution that has this point. So I'm trying to find one of those solution curves, and I want this one specifically. So we are going to separate out our variables, like on the last one, we're going to integrate, and then we're going to use this point to find any constants that we have. So I need to multiply by dx on both sides. And then I'm going to have to divide by y. So I'm going to end up with dy over y because I'm dividing by this y. And then I have to multiply by dx. I'm going to have dx over x squared. And that's what I'm looking at having to integrate. So dy over y is going to just be natural log. That's all set. On the other side, it might help to have the x not in the denominator and write x to the negative 2 power dx. So that's just going to be a power rule. I think what's gotten difficult is just mixing all of these rules together. It seems like so much to remember. So on the left, we have natural log. And on the right, I would have to add 1 to my exponent and then divide by that number. And then I am going to write plus C1 here, some kind of constant. I don't know that it's a really big deal if we label them separately or not. It is just, again, the notation that your book does. So my natural log of y is going to be a negative 1 over x. That's what I really have here, plus c1. And at this point, I could go ahead and put in the 1, 3, or I could keep going. I know I'm not going to want it in this form anyway. I'm going to want to exponentiate. So I feel like it'll maybe be easier to substitute if I do that step. So I'm going to raise both sides as a power of e. We're going to exponentiate e to the negative 1 over x plus c1. So whenever we have this, we're always doing that trick. So the trick I am talking about, so over here, I'm going to have absolute value of y. But the trick I'm talking about is on the right. Remember, if I have e to both of these different powers, we could write it as e to the negative 1 over x power times e to that c1 power. So we're always doing that trick, and then we're making this like one big giant constant because e raised to a power is a constant. And then we don't need to worry about a plus or minus because our plus or minus is going to get absorbed into that constant. So we have CE to the negative 1 over x power. All right, so now we're given that 0.13. So that means I need to put in a 3 for my y and a 1 for my x. So that's going to be e to the negative 1 power. So I divide by e on both sides. I'm solving for c. Remember, e is a constant. We are trying to solve for c. But a negative exponent in my denominator doesn't make sense. It's really just 3e equals c. So then I am going to end up with y equals, so I'm plugging everything back into here. So instead of the c, I'm going to have a 3e, and then I'm going to have e to the negative 1 over x power. And then we're all set. So I guess you could come up with a number for that, but we don't like getting our calculators out, so that's just fine. So in the back, we're going to look at something that's going to seem familiar from the last chapter. Well, not yet. So your book does, and I'm not going through the whole how they derive this formula, the whole derivation of this, but they do talk about a logistic differential equation. And this is on page 427 is where they are coming up with this. And they kind of take you through like finding. So they start out with something like this, which is what we're working with. And then they take you through how to get like this basic formula. And I'm not going to go through that right now. These notes would be way too long. I think I would lose you. I'm going to give you like the short way. So we are going to take something that looks like this, and it's going to look really familiar after I'm done working with it. So we are going to we want to write a model for elk population. Oh, I missed another letter. Elk population P in terms of T. So I'm going to write P equals. Now, whatever this number is here, so you're going to notice that there's a constant, and then there's P, and then there's 1 minus P over something. So that number right there is going to go in the numerator of my fraction. And my denominator is going to be 1. This is going to look really familiar, plus, and then I have BE to the KT power. So this is going to look a lot like those models that we looked at in the last chapter where we were finding the initial and the max and when it was changing the most. So this should look exactly like that. So again, this 4,000 comes from right here. So it has to be set up like this. I have to look at the change in population with respect to time. It's proportional. K is that constant proportionality. K is the same K that's down here. So if they laid this out for you and this was like a 1/3, then I would know this K down here was a 1/3. So those are going to match. And then these two are going to match as well. So those two are going to match and these two are going to match. But it needs to be set up like this. All right, so let's see what we can do with this. So I have a model. The problem is I have two different constants here. I have this constant B and I have K. So I have to read this problem and figure out what's going on. The State Game Commission releases 40 elk into a game refuge. So after 5 years, our population is, I should move my paper down a little bit, is 104. The commission believes the environment can support no more than 4,000. Well, that goes with what we found before, right? We looked at this before and we knew that the numerator ended up being that maximum. So that's what we have here. And this is our growth rate. This was our growth rate. dp dt makes sense. That's how our population is changing with respect to time. So that's the growth rate. So what we can use here is we can use some of the information that we have to come up with these two different constants we need, B and K. So we know that at t equals 0, so that would be initially, we had 40 elk. So we're going to use that. So that means my population's going to be 40. And then I have 4,000. And then in my denominator, I'm going to have 1 plus, I don't know, B, E to the, let's see, K times 0 power. And I know E raised to the 0 power is just going to be 1. So I end up with 40 equals 4,000 over 1 plus b times 1, so just 1 plus b. So think of this back to means extremes theorem, where we're multiplying across our equal signs. So we're going to have 40 times the 1 plus b equals 4,000. So then I would divide both sides by 40, which is going to be, that'll take off a 0, it'd be 100. And then b is going to equal 99. So I used one of those sets of information I had. This should remind you kind of when we looked at just exponential growth. But again, this is a logistic differential equation. So it seems similar, like this part of it is similar, right? But we have this maximum on top. It's not unbounded. So now I have P equals 4,000 over, let's see, 1 plus 99 e to the kt power. So we have some information, but we still need to know k. So let's go back to the problem and see what we haven't used yet. So we used this time 0, there were 40 elk. Oh, but after 5 years, the population's 104. So let's go ahead and plug that information in. So when t equals 5, our population is 104. All right, so 104, we have 4,000 over 1 plus 99 e to the k times 5 power. I guess I need to adjust this document camera a lot here. So to solve, I would look at cross products again. So I've got 104 times 1 plus 99 e to the 5k power equals 4,000. I would divide by the 104. It just gets to be kind of a mess here. And then we'd subtract 1, and then we'd have to divide by 99. Like it just, at this point, I need to probably just come up with a number here. So let's say 99 e to the 5k, and I think I got a number for that before. I did. It was about 37.462. And then I divided by 99, and I got a different number. And then we'd really want to now log both sides. So remember, we're doing all of this just to find those constants from our original model here that we're trying to write. So when we log both sides, and feel free to show a little bit less work when you're logging both sides right now. I'm just worried about missing a step and having someone really confused, especially when you're on your own at home. So k is going to be 1/5 of that. And I really, when I'm putting all this into my calculator, I'm not clearing it out. I just keep doing more steps, and then I'm just rounding it once at the end. So I get k is equal to negative 0.194. So that means my model is going to be 4,000 divided by 1 plus 99 e to the negative 0.194 t power, where t is years. And so this is the maximum the elk population can be. And this is giving me like how it's growing. So I know there's 0, or at time is 0. So right away, initially there's 40. After 5 years, there's 104. So I know the elk population keeps growing, but it can't grow bigger than this. So B is asking me, after 15 years, what's going on? So that means I am going to let t equal 15, and we are finding our population. So we know in 5 years they had already grown to 104. So what is going to happen in the future after 15 years? So it already seems like they've more than doubled in 5 years. So 15 years, maybe they've more than doubled again. Maybe we're going to see like 300 elk. So it's always good. Maybe that's kind of low though, huh? Because those elk are going to make more elk. So it's always good to kind of throw out numbers and think about what's going on. I definitely wouldn't expect a number bigger than 4,000. And I definitely wouldn't expect a really small number. So just kind of think about your number sense here. So I'm using my model. And I have 1 plus 99 e to the negative 0. I can't even remember what decimal I had, 194. And now we're doing times 15. And really, I'm just plugging all of this in, right? I'm not solving anything. I'm just trying to put this in my calculator. And I got 625.675. And so I said about 626 elk. And I know the first time I did this, I didn't round this to 194. I left a lot more decimal places. And then I think I got 629. So depending on your rounding, it could be different. Just make sure you're putting down on your paper what you're really actually putting in your calculator. So 626 elk. So last step C, we want to find the limit as t approaches infinity. And I know we've already talked about this in the last chapter, but we're going to do it again anyway. So I'm writing down my model. And I want to think, what happens to this as t gets really, really big? So as t gets really, really big, I'm raising e to some tiny negative power. And I know if I'm raising e to a tiny negative power, like e to the negative 0.000015, I'm getting a tiny fraction. I'm getting 1 over like 1 million. I'm getting some tiny, tiny fraction that's so close to 0. So the bigger that t becomes, the smaller that this whole thing gets here. And if this gets closer and closer to 0, it doesn't matter that I'm multiplying by 99. If I take a tiny decimal and I multiply by 99, it's still a tiny decimal. So this is just getting smaller as t approaches 0. And so this basically just becomes 4,000 over 1 plus 0, which is just 4,000. And that is our maximum. They also call it, in your book, the carrying capacity. So just some new vocab to throw out there. So that's one of the things we're learning this year in math. It's not like we're just taking one test from a textbook and they're only going to ever use one word. We're prepping for an AP test. We need to be really versatile with our language so we can actually apply the math. So that is the answer on that one. So hopefully you will be able to work on the homework. There was a lot of just separating out the variables like we did on the first side. I think there was only 2 of these problems, like example 10, but I would expect one on your test. So lots to look at, lots of natural logs, lots of E. Good luck on your homework.